Hello everyone, myself Pushpalata, Assistant Professor, Department of Electronics and Communication Engineering, SJB Institute of Technology. Today we are going to discuss about some of the contents related to Module 2 8051 instruction set. We are going to begin with some of the arithmetic operations. The 8051 microcontroller is designed to perform arithmetic operations such as addition, subtraction, multiplication and division. And in 8051, the instruction set supports all these arithmetic computations, both on signed and unsigned numbers, with basically range of 1-bit flags that often basically indicates the status of the computation. Since because the flags are used to know the status of carry generated or any flow control of the particular program. Say for example, I'll just take an example of a subtraction. In case of a subtract operation, we may produce a positive number, or the result may be even a negative number. So based on the number which is being positive, certain section of your user program need to be executed. And if at all the result is negative, then the different section of program may be executed, right? So hence like monitoring of these 1-bit flags that are available in the 8051 architecture, by knowing the status of the program status word which contains all these carry flags, will be used for the computation, and that can be determined, and also we can analyze the program flow control using these flags. Now let us talk about the arithmetic operations. As I told that we have addition, subtraction, multiplication, division. Along with that we can increment or decrement the value in a particular address location, and also we can decimal adjust the value to its BCD. Like we have INC for increment operation. INC, the destination location, the content of destination location is incremented by 1. DEC is an instruction for decrement. So here the content of the destination is decremented by 1. ADD or ADDC is the addition instruction, which is used basically to perform addition of the destination content and the source content. This is ADDC is for addition with including the carry. Here ADD is the addition without carry. SUBB, destination comma source, is an instruction which is used to perform subtraction with carry. That is, you are subtracting source from the destination content. MUL is the multiplication instruction which is used to multiply the contents of register A and B. And we have DIV, that is a division instruction which is used to divide the contents of A by B register contents. And DA is an instruction which is used to decimal adjust the accumulator content. So DAA. NOP is to halt the program for a particular specific amount of time. So no operation. NOP is an instruction which does that particular operation. Now when we talk about the addition operation, uh, we have an instruction, as I told you, ADD, add a comma source, which adds the content of source operand with the accumulator. To take an example, we are having a simple program here. We are moving the accumulator with an immediate value 25H and R2 register with an immediate value 34H. Then when we perform addition of the content of accumulator and R2, the contents are added together and the result is stored in the accumulator, that is the destination location. And using many addressing modes, we can perform the addition operation. Like the source location could be any immediate address, register, or even a memory address location, or the register which is pointing to a specific address location. So here these are the instructions which does addition of A with an immediate value N and perform the addition of an accumulator content with the register content. Here the content of accumulator is added with the content of an address location, and here the content of accumulator is added with the contents of the address in the RP. And these are applied even for both signed and the unsigned addition. Say for example, in case of 8-bit unsigned addition, the number can be added within a range of 0 to 255 with respect to decimal I am talking. Then in case of 8-bit signed addition, the range is from -128 to plus 127 in terms of again decimal. So these are some of the values that you get it as an example we are showing here for signed and unsigned addition for different varieties of or values. Okay, and in case of unsigned addition, all the 8 bits are considered with the magnitude of your content, but in case of signed numbers, the most MSB, most significant bit, is taken as a value which is used to know whether it is positive or negative number. If the MSB is 0, it is positive number. If the MSB bit is 1, it is considered to be the negative number. So the remaining 7 bits are utilized for the number utilization in order to perform the addition operation, and that applies even for the subtraction as well. And these are also some of the examples for performing addition of signed and unsigned numbers. Here what happens is some of the flags are affected when we perform the addition operation, and those flags are carry flag and the overflow flag. Whenever the carry flag is 0 and overflow flag is 0, we are not going to perform any action. The result will be directly stored in the destination. But when the carry flag is 0 and the overflow flag is 1, the result will be, it's nothing but it's a complement. We are going to complement the sign of it. That means if the overflow flag is 1, the complement of signs, say for example plus becomes minus and minus becomes plus. And if at all we have 1-0 condition and we are not going to do any because overflow flag is not set, only carry is there, so carry will be stored in a respective destination location. And we have 1 is again carry is 1, overflow flag is 1, so we are going to complement the sign of a value. So these are some of the flags which gets affected during the addition operation. And with respect to addition using the carry bit, we are having an instruction called as ADDC opcode. ADDC, with all other addressing modes, we can perform the addition along with the carry content. Here content of accumulator added with the immediate value and along with the carry bit. And finally the result is stored in the accumulator. In case of ADDC A, address, here the content of accumulator is added with the value in the address location along with the carry. In the third instruction, the content of accumulator is added with the register content along with the carry bit. Finally, the result is stored in the accumulator. And the last is an indirect addressing mode where accumulator content is added with the content of the indirect address in the RP and along with the carry bit. Finally, the result is stored in the accumulator. Now here a simple example is shown where we are loading the accumulator with the 1CH and take that also R5 with loaded with 0A1H. Now we are performing the addition of A and R5. Finally the result will be stored in the accumulator. Carry flag with respect to this value addition is 0 and overflow flag is 0. Now when we perform the addition again with the modified values of accumulator and R5 value, that means A now contains BDH, right? BDH is added with A1H. The result will be 5EH. Here what happens, the carry flag is 1 and the overflow flag is 1. Now in this situation the result will be, say for example 5EH is there. Okay, so what happens, 5EH, the sign becomes negative. Okay, so in that situation the result will be displayed. Whatever the result is stored in the accumulator will be modified. Now ADDC A with hash 10, that is an immediate value we are adding along with the carry. So content of A is now 5EH. So 5EH is added with the immediate value 10, then along with the carry bit 1. So this becomes 5E plus 1, 5F plus 10, 6F. The carry generated is 0, overflow flag is 0. Next we have ADDC A comma hash 10. The remaining values of 6F, that is the accumulator content is 6F now, will be added with 7F 10, and the result will be 7F, which is stored in the accumulator. These are the increment and decrement instructions, which are the arithmetic instructions. Basically involves adding or subtracting one from the operand. These instructions are very much useful for counting the number of times the user program actually travels through a certain section of code. And also whenever we want to jump to the previous or the next location, we can make use of these operations. Here we are showing some of the examples of utilizing the addressing modes for especially incrementing and decrement purpose. The first set of increment instructions are like this. We have increment A, where we are adding a 1 to the accumulator content. Increment R, we are adding 1 to the register R. Then we have increment address. The 1 is added to the direct address location, which is mentioned. Increment at RP, here 1 to the content of the address specified in the register RP, and increment DPTR 1 to the 16-bit DPTR value will be added. Incrementing and decrementing the port addresses, basically it affects the port latch register, and in that case none of the flags are affected by these instruction. And after any increment instruction is executed, if the register contents exceeds FF, okay, because when the register contents are like say for example FE or FF, and if I increment it and if it is overflows, then they roll over to 00. That means it goes back to 00 if at all incremented FF. We have certain decrement operations like decrement accumulator, register content, and add and decrement at RP. These are the values of the destination is decremented or subtracted by 1. And here whenever we are performing the decrement operation, if the register contents goes below the 00, then they roll over back to FF. That means 00, if you want to decrement it, it goes back to the FF value. Only the DPTR register, which is a 16-bit register, which overflows from FFFF to 0000. So the increment and decrement instructions are very much used, or quite oftenly it is used for counting events, counting program flow through a particular section of user programs. Some of the example which we have shown here, basically accumulator is loaded with some immediate value, that is 3A. We are decrementing it, so it becomes A becomes now 9. So decrement A, the value now becomes 39. We are loading the R0 value, R0 register and 15H address location with 15 and 12 immediate value respectively. When we increment at R0, what happens? The content of R0 is 15 and it is getting incremented to the next value, that is 16, right? So here when we talk about decrement 15H, what happens is, so once again, here in the increment at R0, that means R0 is having 15H, at R0 is pointing to 15H address location. So the content of 15H, that is the address location content is 12, that will get incremented, that becomes which is 13. Then when I perform decrement 15H, the content of the address location 15H is 13, which will be decremented or subtracted by 1, and that is 12H. When I again perform increment R0, R0 is having 15 and that gets incremented to 16. So there is a difference between indirect addressing and direct addressing, so which is clearly understood here. We have next instruction move 16H, A, which taking the content of accumulator, that is 39H, which is accumulator content, to the address location specified as 16H, and incrementing at R0. At R0, now the value of R0 is 16H because we have incremented it. Now 16H, at 16H we are loading the content, that is accumulator content 39H. Now again it is getting incremented to 3AH. The next instruction shows moving a value, immediate value to the 16-bit DPTR, that is 1 to FF. Now when I increment 16-bit DPTR, that becomes FF gets rolled down to 00 and gets incremented with the next one. So 1300 will be loaded in the DPTR. When I decrement 83H, so 83H is a SFR of DPH, so 13 becomes equal to 12. Okay, only the 8-bit, because we are talking about only 83H, right? 83H is only the higher byte of your DPTR. That gets decremented or subtracted by 1. And finally, the result will be stored back in the DPH. These are some of the instructions related to subtraction. All the instructions which perform subtraction, they use the A register as the destination for the result. And all these instructions, they use borrow bit, which is same as the carry bit, carry flag in the program status word or program status register for basically performing the subtraction. And here the carry flag is set if at all the borrow is needed from bit 7 of the value, okay, for subtraction operation. And carry flag is cleared in other case. That means if at all I don't want any borrow, the carry flag will be 0. Similarly, we have something called as overflow flag. This overflow flag is set if at all borrow is needed from bit 6, but no borrow is required from bit 7. Okay, say that I have 10111101. Okay, so whenever I am performing okay, subtraction, something like this. So whenever there is a borrow from, when borrow, it's required for bit 6, okay, needed for bit 6, but not for bit 7. Okay, so in that situation, a overflow flag will be set. Overflow flag is also set if at all there is a borrow from bit 7, but no borrow from bit 6. Okay, that means bit 7 is required borrow, but bit 6 is not required. So that time overflow flag will be set. So in all the cases, overflow flag is clear to 0 apart from these two conditions. Now during this arithmetic operations, basically it is a very good practice to clear the carry before performing any operation. Since most of the operations of arithmetic instructions, they affect the carry flag, and some instructions they use the carry flag information. So basically it is very important to clear the carry before we actually perform the subtraction or any arithmetic operations. Here we are showing some of the examples for using different addressing modes. SUBB A, #n, where we are subtracting the immediate number and the content of the carry flag from A value. So and finally put the result in the accumulator. Next is we are subtracting the content of the address location which is mentioned along with the carry content from A register. Put the result in accumulator. Next, SUBB A, RR, where the content of register R and the carry flag will be subtracted from accumulator. And here subtract A, at RP, subtract the contents of the address in the RP along with the carry from the accumulator, and finally put back the result in the accumulator. So we can also perform signed and unsigned subtraction, for which we are showing a small example. And we know that for signed or unsigned subtraction, especially for signed subtraction, we make use of the most significant bit as the sign indication. And for unsigned, we don't require any such things. Here, as I told you, the high MSB is mentioned for the sign indication. The remaining bits will be taken for the performing subtraction operation, and some examples are shown here. You can just go through it. Related to subtraction operation, we are having a simple program where we are loading D0 address with 00. That means D0 is the address location of the carry, which is cleared to 0 because as I told you, carry flag should be cleared before we perform the arithmetic operations. Move A, #3AH, where 3A is an immediate value which is loaded to accumulator, and 45H address location is loaded with an immediate value 13. Now what we are doing, we are subtracting A comma 45H. 45H contains 13, and that is along with the carry is already 0, and accumulator value is 3A. Now what we are doing, we are subtracting the content of that is 13 plus 0, which is equal to 13, from the value of accumulator, that is 3A, right? So this becomes 27, which is loaded back in the accumulator, that is 27H. Now we can also perform similarly one more time, and SUBB A comma hash 80. Now A is having the value, that is say for example 14H. Now what we are doing, 80H is an immediate value, along with the carry is 0, and now that will be subtracted from the accumulator content. But what happens is accumulator is having 14H, right? When you are subtracting 14H, when you are subtracting the content of 80H, then along with the carry is 0, so that is 80H. Okay, let me write it here. So 14 subtracted from 80. So when we are performing this particular condition, I require a borrow, right? So let me elaborate this content or the stuff. That is 4 is 0 0 0 1 0 0, then 0 0 0 1. Now 8 is 1 0 0 0 0 0 0 0, right? Now when I do this, it becomes 0 0 1 0 1 0 0. There is a borrow which is required for the 7th bit. In that situation, overflow flag will be set to 1, and what happens is when the overflow flag is set and this becomes equal to in the binary subtraction, this is taken as like 2 minus 1 will be taken as will be taken as 1, right? And this is 1. So finally the carry flag will be again set to, because borrow is already taken, right? So borrow will be set to 1. We are using the carry itself for borrow, and later we need to again go for complementing the sign, because your carry flag is 1, overflow flag is 1, both are 1. Complement this sign, so the value becomes now it's equal to 94H. Only 4 is there, right? So this value is it becomes 0 1 1 0. So 0 1, yeah, complementing the sign. So complementing the sign would be negative, right? Because 1 is there in the highest, most significant bit, so that becomes 0. Then after making it 0, okay, what we are doing, the value is 1001. It is 94H. Now A is loaded with 94H. Then carry flag is set to 1, overflow flag is set to 1. Only the sign will be complemented. In the second case, let us analyze still more, where the accumulator content will be subtracting the value of an immediate value, that is 22. Now accumulator is having how much? 94, right? It is going to subtract 22 along with the carry, so that is 23, right? So 23 has to be subtracted. So this becomes 1 0 0 1 0 1 0 0, and 0 0 1 0 0 0 1 1, right? So when I am performing this, I would get it something like this: 1 1 1 0 1 1 1 second, just erase it, let me write it. So 0 minus 1, I have to take up a borrow here, so 2 minus 1, it becomes 1, right? This is 0, then this is already 0 because 1 I've taken here, borrowed here, and this is 0, right? And 1 1, here it is 0, right? So this is 0. No, 1 second, here I have to take a borrow. So in that situation, 0 minus 1, 2 minus 1, 1, then here it is 1 is there, right? So this becomes 1 and this is 0, so totally it is now 71, right? So the result is now 71, which will be stored in the accumulator. Similarly, when I perform with an FF, okay, so let us see what happens with this. So now accumulator will be having 71, that is 0 1 1 1 and 0 0 0 1, right? Now what happens is you are subtracting FF, so 1 1 1 1 1 1 1 1. Now what happens is 1 minus 1 is like 0, and here I am supposed to take a borrow from the fifth nibble, that is 1 minus 2 minus 1, it is 1 0 0. Then already I have taken this, so I have to take a borrow here, which becomes 2 minus 1 1, and this 0 minus 1 again I should take 2 minus 1 1. Okay, now there is a requirement of carry from borrow from the seventh nibble. So in that situation what happens, 0 1, I have to ask for a borrow, right, from the C bit, right? So what happens now, C is set to 1, okay, borrow will be set to 1, then this is going to transfer 2 minus 1, it is 1, and now here 1 is there, now 1 minus 1 will be set to uh, 0, because this fellow is going to give 2, right? So where he will take, he'll borrow it, okay, because here also 0 it is there, so borrow is required. So it gives 2 here and 1 here, so like 2 minus 1 becomes 1 and 1 minus 1 becomes 0, so the total answer will be now 72H, right? So this is how the subtraction with the borrow case will happen. Now we have next multiplication of unsigned numbers. Basically we make use of MUL, that is the multiplication instruction, which we use it for multiplication operation. 8051 basically it supports multiplication operation with one instruction, that is MUL. Here we are going to use A and B register, and finally after multiplication the 16-bit result will be stored in B and A. And here what happens is the content of the lower byte, once an unsigned number is loaded in the A register and second unsigned number is loaded in the B register, the multiplication instruction has the following format, which I have shown you, like mul A B, right? And mul A B, which multiplies A with B content, puts the lower byte in the accumulator, okay, and higher byte in the B register, okay. So basically when you perform 8-bit numbers multiplied, you get a result of 16-bit, okay, so which is stored in with respect to 8 bits in the A and B register both. Here what happens is when you perform the multiplication of 8-bit numbers, overflow flag may be set, okay, if the result is greater than FF, okay, and carry flag will be clear to 0. Let us take an example here where I am loading an immediate value accumulator A with 25, and I am loading the accumulator B register with 65. When I perform the multiplication operation, the value is 0E99H, where 99 is loaded in the accumulator and higher byte is loaded in the B register. Here, this is an table which shows that multiplication, like byte to byte multiplied, A and B content, lower byte in the A and higher byte in the B register. This is a simple example to show the multiplication operation where I am loading A with an immediate value 7B, and B is the address location which is having F0, which is loaded with an immediate value 02. When I perform multiplication of A and B, 0, that means when I perform 02 with 7B, the result will be like 7 F600, where the accumulator is loaded with 00 and B with F6, where overflow flag is set to 0. And in the second condition, when I take A with FE value, okay, and if I multiply FE with B register, because B is already having F6, right? So what happens is there is a overflow which happens, which is crossing FF, right? So in that situation, overflow flag will be set to 1. Next, we have division of unsigned numbers, and 8051 again supports division operation with single instruction. In this instruction, the registers A and B are used. The first number is loaded in the accumulator and the second number is loaded into the B register. When we perform div, that is division operation, the unsigned number which is stored in the A will be divided by the B value, and finally the the results will be put in A and B. That means when you perform division operation, quotient will be in the accumulator, remainder will be in the B register, right? So quotient will be stored in the A and remainder will be stored in the B register. This is an example where I am loading A with 95 and B with 10. When I perform the division operation, 95 will be divided by 10. So in that situation, what happens is 10 9s are 90, remainder becomes 5. 5 will be loaded in the B register and 9 is the quotient which is loaded in the accumulator. One more example to show the division operation where I am just taking up accumulator with 0FFH and also loading B with 2CH, that is F0 is the address location of B. When you perform division operation, the resultant, that is quotient, will be stored in the accumulator, B will be loaded with the remainder. And this is how we are going to perform the division. And the last, what happens is when I check that the resultant from the third division, you see that A will be 0, B will be 0, and again if you perform division of A by B, what happens is it is 0 by 0, overflow flag is set to 1. Basically what happens is overflow flag, it will be cleared to 0 unless B value holds other than the 0, right, before the division operation. But when the B is holding 0, okay, then overflow flag will be set to 1 before the division, right? So if the B register is having 00H before the division, the content of A and B are undefined after the division. So this becomes A and B are undefined, and immediately the overflow flag will be set to 1, and the carry flag is cleared to 0 after the division. So this is how it works with division operation using the 8051 microcontroller. Next instruction we have decimal arithmetic, that is decimal adjust arithmetic instruction. 8051 performs all the arithmetic with the binary numbers, right? So basically what happens, programmers, they use hexadecimal numbers to write the binary numbers in compact format, right? But here what happens is, in order to represent the decimal numbers in microcontroller, we may have to use the numbers between 0 to 9, right? So I can represent it using the 4-bit digits 0 to 9. We can represent it with say for example 0000 to 1001, right? So 0 to 9 I can easily represent it using the binary digits. Even you can think of like above exceeding 9, right? So what happens, it fall into the region where I have to write it as A to F, right? 10 is A, 11 is B, like that up to F, right? So but in case of BCD representation or BCD arithmetic operations, okay, in that situation BCD numbers are like binary coded decimal numbers and they are valid only for 0 to 9. Whenever it is exceeding 9, or I cannot just represent it using A and A to F, right? So 8051, it provides a special instruction that will add 6 to the result, okay, of particular numbers which is exceeding that 9 value, okay. And this instruction has a format, okay, which we call it as DAA. What we are going to do, whatever the result you have, you will be loading it in the accumulator. That means if it is exceeding the 9 value, and you are adjusting the sum of the two packed BCD digits in the A register, okay. That means if it is exceeding 9, no, you will add 6 to it and you will adjust that value below 9 or below A. The result will be stored back in the accumulator, and this instruction, it adjusts the 8-bit value in A, which is resulting from the earlier addition of the two BCD numbers. Okay, I'll take you an example and explain this DA instruction. And if the accumulator bits, that is 0 to 3, if it is greater than 9, or if the auxiliary carry flag is set to 1, okay, then the number 6 is added to the BCD digits which is stored in the um, accumulator. And once you add number 6, okay, the BCD digit which is produced, that producing the nibble, that is ranges from 000 to 1001, uh, this particular addition, okay, they would set the carry flag because 1001 is 9. Next number has to be like higher value, right? So that has to be taken and stored in the carry flag. So if at all the carry out propagated all the way through the 8 bits, in that situation I'm going to set the carry flag. If the carry flag is now set, or if higher order bits exceed 9, the higher order bits are decimal adjusted by again 6, okay, to produce basically a proper BCD, packed BCD, which is ranging from 0 to 9, okay. So here the carry flag is set if at all there is a carry out from the higher order nibble, right? Okay. Um, there are some certain conditions for this also. I'll just let you know. A C flag is set to 1 if the adjusted number which is exceeding 99. Okay. And auxiliary carry flag is set to 1. It's used, okay, by the DAA instruction. And overflow flag is not at all affected in this. Okay, and this instruction performs one of the following operation. Either it adds 0006 6066. Okay, it is not that I'm supposed to add only 06, fine. So it can perform either of the condition, like I can go with 0006 60 and 66. So both the sides, that means the higher nibble or the lower nibble, if it is exceeding 9, no. So in that situation you can go for adjusting the accumulator to confirm the BCD number. And DIA does not convert hexa number to BCD number. Keep in mind, it does not convert hexa number to BCD number, and it is not applied to the subtraction. Okay, this is the decimal adjust accumulator, and which is not holds good for subtraction operation. Okay. One example to show that DAA instruction, we are loading A with 42. 42 is a BCD value. Now I'm adding A with 13. So 42 will be added with 13, which becomes 55. Okay. Now 55, when you perform DAA, it will add only 00. So 55 will be there, right? Now again I'll try to take that 55 value, I'll add it with 17. So in this situation what happens, 5 and 7 is 12, so it becomes C, right? And this is 6C. and which is exceeding, it's not a BCD. Now what I'm doing, this will be added with 06 in order to perform or convert it into BCD format, because I'm doing basically a BCD addition here. So what happens is C is nothing but 1100 and 06 is 0110. When you perform this, okay, especially I'm talking this particular thing because 6 is within the range of 0 to 9. What happens is 0 1 0 1. Sorry, I am performing 1100 with addition with 0110. So when you perform addition 010 and this is 0, okay, there is a carry which is nothing but 1, right? Okay, so what happens, you get it as 2. This 1 will be added here. 6 plus 1 would become now 7 2. So 6C is now 72 in BCD, right? And yes, you can also perform ADDC here. Okay, so A is having a value which is 72, and you can add it with 3 4 along with the carry which is initiated as 0. And similar operations can be performed with any variables or any values, immediate value, in order to set it to a 2-packed BCD numbers. Summary of all the instructions, arithmetic instructions, what we have seen. We have addition operation where ADD instruction is used in order to perform addition of accumulator with the source. Then ADDC is we are performing addition of accumulator with the source content along with the carry. Finally, the result will be stored in the accumulator. DAA instruction, it is basically to adjust the binary result of by adding 2 BCD numbers in the accumulator register to adjust the carry flag and also adjust the carry flag. DEC is a decrementing one the content of the source or the destination, whatever we have, and whenever it is 0 0 it will roll over to FF. Then we have div AB. We are performing the division of a byte A and byte B, where the quotient is stored in the accumulator and the remainder is stored in the B, and we are going to set the overflow flag bit if at all B will be equal to 0 before the division, and the result after the division A and B will become undefined. And we have increment source, that is we are going to add 1 to the source, and whenever it is having FF it will roll back to 0 0. If at all we are incrementing DPTR, that is FFFF, it will roll over to 0 0 0 0. Then we have mul AB. We are performing the multiplication of the content of A and B, where the result of A and B will be stored lower byte in the accumulator, higher byte in the B register. And we are going to set the overflow flag if at all it is exceeding the value of FF. Then we have seen the subtraction operation, where subtracting the content of source along with the carry by the content of accumulator, and the result will be stored in the accumulator. And basically we are going to adjust the carry and overflow flags with respect to addition and the subtraction. Almost all the arithmetic operations will be affected with the flags.